Hello, everybody. Welcome to SRA 365. I'm, of course, Professor S. This is this week's lecture. Today, or this week, what we're doing is we're talking about normal distribution, and I will get into what that means, how we interact with it, and then also some tips for working on the lab. Anyway, so let's kind of talk about that. First, we'll talk about the normal distribution, then we'll discuss z-scores, and then using R along the way. Okay? So anyways, normal distribution. It's a thing. We talked about it a little bit in the last lecture, but in order to kind of really understand it, we got to kind of talk about probability, specifically discrete probability and continuous probability. Okay, so discrete probability, that is for probability for countable thing. Continuous probability is for uncountable things. Not super helpful, right? Let me give you an example. Say we're talking about a apple orchard, right? And there's two different probabilities that we might be concerned with. The probability of growing 500 apples and the probability of making 14 gallons of cider. Now, one of these makes way more sense as discrete probability, and the other makes more sense as continuous probability. The one that makes the most sense as discrete probability is the probability of growing 500 apples, where the probability of making 14 gallons of cider would be more continuous. Now, here's where the countable is. Notice that with the apples, when you grow an apple, you grow an apple. They're distinct, right? You don't go do partial apples. There's either 500 apples or 499 or whatever, right? I mean, like there's so many apples. You can count them, hence countable. That's what would make that more discrete. Now, granted, in an orchard, they probably measure in pecks or in, I don't know, some other bigger thing. Maybe they measure it in weight, in which case continuous would make more sense. But as far as this example goes, that would be a discrete probability. The continuous probability, the reason why the cider is a thing is because cider can only be partial, right? Think about like instead of just 14, let's just look at 1 gallon, right? 1 gallon, like if you measure 1 gallon, you can try to be as exact as you can, but it will never be perfectly 1 gallon. There's always rounding that occurs. And the idea is like with these continuous things that have measurements that are always rounding, that's where it becomes a the continuous values. Now, with different probabilities, there's different distributions that we apply. We're going to assume that there's a normal distribution that it goes with this continuous probability. There's other distributions that we could use, but let's just assume that typically we get 13 gallons of cider that we can make each year, I guess, with a 3.2 gallons standard deviation. So that means that 68.26% of the time that we make cider, we can expect it between 9.8 gallons and 16.2 gallons. 95.44% of the time we can expect to get between 6.6 gallons and 19.4 gallons. And almost 100% of the time we can expect to get 3.4 to 22.6 gallons. Okay. So, I mean, it seems like a huge spread, but it gives us something to work with. And that's kind of a lot of the reason why we like normal distribution is because it gives us something to work with. Now, let's kind of take a look at this further. The idea that the probability that I had asked before was like, what's the probability of making 14 gallons of cider? And to kind of understand that, we got to kind of understand a little bit more about continuous values. So here is 14. It'd be around here. I estimated all these. I didn't measure any of this. So if this is about 14 gallons, the probability of getting 14 gallons is 0%. Let's kind of talk about this a little bit more. Like this is what I'm talking about with the continuous values. So first of all, we got to kind of understand infinite numbers in a weird way. So we're going to talk about all the infinite numbers between 0 and 1. And let's say that we have a person there at 0.5 and thinking about the probability of that apple, hitting the person right on the head. We want to know the probability of that apple going to that 0.5 in that line, right? So to kind of understand what that is in between 0 and 1, think about like the amount of real numbers in between 0 and 0.5. There's infinitely many above it and there's infinitely many behind it. And the thing is like with the infinity, like first of all, infinite is not a number, it's a concept. Second of all, it doesn't really matter that it's in the middle of the line. It could be anywhere in the line and there'd be infinite ahead of it, infinite behind it, because that's the way infinite works. And because there's so, like, not just so many, but there's infinite in either direction, that space, that 0.5 takes up zero room. So that means that the probability of hitting that 0.5 in range between 0 and 1 is 0%. But the thing is like if we think about like somebody actually getting hit with a apple, like that apple has to go somewhere, and it does seem possible. So it seems weird that it's 0%, right? But the reason why that's possible is because not because it's going to hit that 0.5, it's because it's that range that we care about, right? That person takes up space, that apple takes up space. It's the 0.5 doesn't take up any space. It's a single point on that line. When we talk about a range of points, that's when we start taking up space. So really the idea is the probability of hitting that person is much greater than 0 because it's a percentage of the area. And that's like what we're doing with this whole probability of the normal distribution, is thinking about percentages of the area. So once again, the probability of making 14 gallons of cider is 0% because remember, 14 gallons takes up no room on here. And so really, when we're looking at 14 gallons, we do some rounding. So maybe we should incorporate that rounding into the values that we're looking at. So maybe a range that we might find more acceptable would be between 13.9 and 14.1 gallons, right? So what's the probability of getting 14 gallons, or about that much, right? And so it ends up being about 2.37%. And that may seem a little bit low, but in case you're wondering, the area between 14.9 and 15.1, which is like further down the bell curve, is less. That's 2.05%. Okay. So anyways, the idea is that like we might we use the normal distribution for find different probabilities and stuff like that, or different things that we might expect. Applying this to other things that we might ask is like, what's the probability of at least 14 gallons? In which case that would be 37.73%. Or if we want to know that it's more than 14 gallons, and that would be 62.27%. Or maybe we want a range, and so instead of just 14 gallons, maybe we want it to be between 13 and 15, because I mean, after we're dealing with lots and lots of apples, so there's probably a huge range, right? Hence why the standard deviation is 3.2 gallons, right? So anyways, the probability of 13 and 15 gallons, or the of getting between that, is 23.4%. Now, before I move on, there's one more thing that I want to talk about, and that is like the less than and less than or equal to. So remember, the 14 takes up no room on our little number line. So if we're thinking of the probability of it being less than 14 and less than or equal to 14, that's the same thing as far as we're concerned, because remember that 14 doesn't take up any room. Okay. That's not always true for like discrete probability. But as far as we're concerned in this normal distribution, it doesn't really matter. Okay. So anyways, normal distribution. one of the great reasons why we like normal distribution is because of this relationship with the standard deviations, that we know that area around the center based upon the standard deviations. Like one standard deviation is about 68.26%. Two standard deviations incorporates 95.44%, and three standard deviations is practically the whole thing, right? And so, anyways, knowing these assumptions, we can answer some questions. So here, I'm going to give you some questions. I'm going to give you 3 questions, and you can see if you can answer these on your own. And I'll have some visual aids as we go along here. So anyways, how much is less than 75? Okay, see if you can do it. And all you need is just this thing. You don't need to use tables or anything. All the information is provided here. All right. Well, anyways, like I said, on top of the knowing that the middle amount is like 68.26%, is that one standard deviation away. It's that it's even between them. And so one of the things is like the mean is 65, and that is halfway through. So anything above or below would be 50%. So anything above 65%, or sorry, above 65 is 50%. Anything below 65 is 50%. So if we consider this to be 50%, then the only other part that we need to really figure out is this part right here, and add it to 50, and that gives us our value. So the way that we find out what this area is like we just divide the 68.26 in half, which is about 34.13%. Add that to 50, and we get about 84.13%. Okay, so next question. How much is greater than 85? Look at the what that area is. It's this value right here. Okay, so we could add things together, but I'm going to show you a slightly different way. So we know that 65, anything greater than 65 is 50%. And also, kind of with a hint of what we did last time, is that if we divide the 99.74% in half, we get or the 95.44% in half, we will get 47.72%, right? So that's up into the 84. And I mean, I know this is highlighting everything but that left right of the mean, but that's kind of the point. If we know that it's 50% and we know that this portion is 47.72%, we can just subtract that from the 50 and we get 2.28%, which is what our answer is. Now, finally, how much greater is 45? And so it's this area right here. The answer, it's on the screen, it's 97.72%. Okay. Now, this is great when we're talking about the amount of standard deviations, but like, I mean, if you notice that the values, we have 65, 75, 85, there could be other values there, right? So there could be like 66, 70 even, right? How do those incorporate? Enter in z-score. So z-score helps us work with areas. The way that I like to think about it is z is the amount of standard deviations away from the population mean in the normal distribution. Okay, so far we've been using z's. It's been 0, 1, 2, and 3, or also -1, -2, and -3, right? But there's other values that we could use. So like the two equations that I have up here is just solving for x, it's the population mean plus the z times the standard deviation, or we could solve z by the x minus the population standard deviation, or population mean divided by population standard deviation. Okay, so I mean, that's how we can go back and forth between x and z. Okay, now for doing the lab, you're given, there's 2 ways that you can do it. One is using the given table, 2 is using R. I'll show you how to do R in a little bit, but first let's kind of talk about this table. So the table, it gives you 3 columns, the z-score, so you can look up the different z-scores. B is the area between the mean and z, and C is the area beyond z. Now, note that B and C are both percentages, right? So it's not, so notice that when z is 0.10, notice that in B, the value is 3.98. That's 3.98%, not a decimal, because if we're thinking about the area under the curve being 3.98, not as a percentage, that's impossible, right? Because remember, the area under the curve is 1 or 100%. So anything above 1 is ridiculous. So in order for you to communicate to me that you know what you're talking about, if you give me a decimal, make sure it's equal to the decimal, like the value less than 1. Or if it's a percentage, make sure you give me a percentage, right? Or make sure you say that it's a percent. Use that percent sign, okay? And I'll use that here so far. So anyways, here's an example of a question kind of where we'll use the table to figure out some stuff. So police department uses exam as part of their promotion process where officers have scores higher than 80% of those taking the exam should be considered for promotion. So 2 officers write their exam. Officer 1 receives a 76. Officer 2 receives a 52. So population mean is 62. Standard deviation is 11. So we need to calculate the z-score, and we want to know what is the score. Was this score high enough to be considered for promotion? So we need to also figure out what would be 80%, the upper 80%. Okay, so first of all, kind of thinking about what that is like if we think about our bell curve, we think about what would be 80%, and we can figure out what the value is. Before we get into what that value is, let's calculate our z-score for officer number 1. So remember, to find z, it's x minus the population mean by standard deviation. And so we just plug those values in, and we get about 1.27. Okay. The area of the possible z for the whatever it's called, that they're trying to beat, ends up being about the z that they're trying to beat ends up being about 0.8416. But we'll talk about how to kind of get that with the table. See, the thing is like, remember, with what we're given beyond the mean and in between z and the mean. So here's the mean, and remember, 50% of the is to the left, and then there would be 30%. That would mean 30% is to the right for this whole area to equal 80%. Right. And so since we know that 30% is the number that we have, I mean, we could do the beyond the z, but we really want to just do that area in there. So we're looking for this portion right here. That's column B, that area between z and the mean. So when we look at the table and we look at for what values, 30 doesn't come up, but we get a 29.95 and a 30.23, which is somewhere between, means the z is 0.84 and 0.85. So which one is it closer to? Well, if you think about which one is 30 closer to, the 29.95 or the 30.23. So notice that the first one is 5/100ths away, and the other one is 23/100ths away. So the first one is closer, right? So we'll just go with that. So that means our z-score is 0.84. And so since 1.27, that's the z-score of the officer, the first officer, is greater than the 0.084, we know that they are high. It's high enough for promotion. But then what about the second guy? And so the idea is like when we plug those values in, we get that person has a value of negative 0.91. And so remember, that's their z-score. So that means that when you do the population mean minus 0.91 times the standard deviation, that's where you get the 52, right? We don't need to go backwards like that, but comparing that z-score with the 80% z-score, negative 0.91 is less than 0.84, so we know that they're not able to get a promotion. Okay. And again, we're able to do that. We're knowing that the z-score of about 0.84 would be here using the mean of 62. And so it's just plugging this in and is 0.84. So that means the value for that thing, that the value, the test score would be 71.24. Okay. Now, to do this in R, we have two methods to help us with this, pnorm and qnorm. So pnorm is helpful when we're trying to find the percentile. Qnorm is when we're trying to find that value on the number line, that value of x. So when we're using pnorm, we use the value of x to get the percentile. When we're using qnorm, we're using the percentile to get the value of x. And other than that, we use the same information, right? Notice that the lower tail true and lower tail false is the direction either to the left or to the right of our value to get that area underneath is what it's referring to. So for to get that, to find out what that area, we have lower tail true for the pnorm, and given that area, depending on if it's to the left or to the right, that's what the lower tail is referencing. Okay, so if I plug this in here, so Z would be finding the same way as before. But that 80%, well, that's just plugging it in. We just plug in that 0.8 because that's 80%. 62 is the population mean. 11 is the population standard deviation. Lower tail is equal to true because we want to go to the left. And we find out that when we press enter in R, we get 71.25783. Right? And so when we plug that into our formula for Z, we get the 0.8416. Remember when I gave that answer before that was more exact? That's because I did it in R. To do answer number 2, I mean, it's like the same thing because we're just finding that 80% area would be the 71.25783. Anyways, this is just to show you how you can do it in R. If you don't have R set up yet, you're not required to. You don't need it for the lab. I just think, like, why not just start using it? Okay? It helps. I think it's easier than reading the table because you just enter the values in. You just have to know how to interpret the results and have to know how to enter in the values. So hopefully this helps. Anyways, I think that's good for today. I'll see you all later. Bye. Hey everyone, hope you enjoyed that video. If you did, please press the like button below. It lets me know I'm doing something right. If you have any questions about any of the content, please send a message to both me and the rest of the teaching team in Canvas and we will get back to you as soon as possible. Don't send it through normal email, you will not get as fast response. If you have any suggestions for how I can make these videos better, please leave in the comments below. Don't forget to roundhouse kick the subscribe button and ring the bell to get notified for the next video. Anyways, I think that's good for now. See y'all later. Bye.